Okay, so I think we have a discussion on K values. There was a couple of questions during the break. So K values. So what was your question?
So my question is, like, for example, at convergence pressure, we have K values equals to 1. So what is the physical meaning? Like, does this fluid becomes critical? Like, all components try to go into the gas phase or the liquid phase?
Okay, so convergence pressure. This was also a comment or question by another one during the break. So I'll try to talk about this a little bit. I'm going to make a sketch over here. Try to make a sketch. Pressure on kind of a log scale, and K values also on a log scale, 1. And then I'm just going to draw for 2 components to make it simpler. And we should have this, the slope of this should be -1 at so this would be for any component. Probably it'll look like that for any component greater than with 3, 4 carbon numbers. Okay. And then you've got for methane, so for methane you've got it coming down again kind of with a -1 slope, and then it'll probably bulge out and then come back down. I wanted these to come together here. Let's try to make this work a little better. Man, got a new pen here. So. And all of the other, so this might be methane and all the others, and they all end up converging, and I call this the shape of the nose, okay? And every reservoir fluid system is going to look different and have a different shape. This might not have in and out. You might get another reservoir that, comes in like that. At the lower pressures, it's the same, and then maybe it does something like that. So the shape of the nose in this case is different, in addition to the convergence pressure being different. Okay? And obviously at the convergence pressure, all of the K values approach 1, meaning that the equilibrium composition of gas is equal to the equilibrium composition of the oil, at least approaching each other. So this is for a given composition. This system, you have composition 1, and you have another composition 2. Okay, 2 different compositions. I'm going to stop doing both, but okay, we got a particular composition has a particular shape. Now, let's look at the pressure temperature diagram. Of this particular composition. I'm just going to take, 1, I guess, the first one. And we're going to plot the pressure temperature diagram and make it look kind of normal looking. And this kind of thing hugs not 0, but very low values. And I'm going to put the critical where? I'll put it here. Okay. So that's the critical point of this mixture. Now the K values over here is for a particular mixture and at a fixed temperature. Okay? At a fixed temperature. Have I lost anybody? We've got a given composition that has a pressure temperature diagram shown on the left. We've got a K value pressure diagram on the right for that same composition. Let's say the solid lines here. Okay? If by chance the temperature that we're plotting the K values here, if that temperature happens to be the critical temperature of the mixture, okay? Let's say that the temperature on the right happens to be that critical temperature. Then that convergence pressure, if this is the case, then the convergence pressure, well, let me just, this is labeled PK. Then the convergence pressure, PK, is equal to the critical pressure of the mixture. It's a physical condition. Okay? If you had an accurate enough experimental equipment, you could actually bring the system to that pressure and temperature just slightly on the inside of that point and get two phases. You could measure the composition of each phase and you'd see that those two phases are essentially identical. Okay? You could physically measure the system. Now I'm going to change colors just to make this a little more. So now let's take, for the same system, this temperature. Okay? Well, if we change the temperature, then the two lines I've drawn are going to look different. Which is okay. It's just going to get a little bit messy. So, because it's a higher temperature, we're going to get, this is going to be looking like that. And it's going to turn around. But now, what could very well happen is that it might get a convergence pressure out here. But this is the bubble point, right, of that composition at that temperature. And that pressure might be down here. I'll change this as well for methane. It goes up higher. Okay. So this is the system 1 at a different temperature, T.
You decrease the temperature.
Decrease the temperature.
So why did you increase the vapor pressure?
Not the, oh, let's see it. Oh yeah. Because I'm still on Indian time. Yeah, okay. Yeah. What am I going to do? Okay. Man, you're not supposed to correct the professor. Don't you know better? You're not going to get an A in this class. No way. Okay. He's right. because the vapor pressure at a lower temperature is lower. Okay, so it's going to cross the point here. So the point of this comment Bilal made is that you don't want to do what he did because you get me real upset. And you don't want me upset, right? Okay. So let's see what we got. Okay. I'll try again. Lower me down like that. Goes like that. And this one here is going to be lower too. Okay. I don't really like the way that looks, so I'm going to take it away and do it a little bit differently. Something like that. Okay? So it's at a lower temperature. And the bubble point, at least I got that right. I put that down here. Now, what that says is that out here, you know, everywhere out here, this is single phase. There are not two phases, okay? So we can't make measurements out beyond there. So this is Curtis's fantasy, that there's a convergence pressure out here. Beyond the bubble point, we don't have two phases. So how can you get a Ki and a Xi and Y to say that the convergence pressure is out there? Physically, you can't measure it. So physically, the only K values that you have are the solid purple lines, and they stop at this point here. They stop there. So if we measured K values, you could measure them along here, but you could not measure them at pressures above that point. Okay? Now, when people like Standing, who actually spent their 4 or 5 years doing a PhD, making measurements of the K values for petroleum systems, and they plotted them up, what they consistently saw was that all of these, for the 20, 30 components that they measured, all of those K values seemed to approach a convergence pressure. When they made the plot, it looked like if you extrapolated that one, it would go to a convergence. If you extrapolated that one, it would go to what looked to be the same convergence pressure. So what they called it originally was the apparent convergence pressure. The apparent convergence pressure. If you read the book by Standing, that's what he calls it. Because unless you are at the critical temperature of the mixture, in which case the convergence pressure is the critical pressure, all other temperatures left and right of the critical, you cannot measure K values out to a convergence pressure. So it's an apparent convergence pressure. But they always seem to be appearing to converge. All right? So that's what we call that. So okay. All right. And that's because out in this region here, it's single phase, right? Out here as high as you want to go. And let's say this is our convergence pressure here that Curtis sketched, extrapolated out into the higher pressure range. So that's the convergence pressure for this system. And the way I've drawn it, it seems to be, actually I'm going to draw a little bit lower than that. I'm going to put it down here. There seems to be a significant temperature dependence in the way, at least if this drawing is, okay. It's not the same for every temperature.